One of the simplest and most reliable ways to check a logical deduction is to form a truth table that includes all of the premises and the conclusion. So, in the deduction that we did earlier, we said our premises are, okay, S implies T, T implies D, and S is true. So those are our premises. And so what I'm going to do is I'm going to create a truth table that has all three logical atoms, so the three individual propositions, and as well as any premises that I need to form. So for example, here's premise one, here's premise two. Premise three is just S itself. I don't need a new column for that one. And then the conclusion is D. Okay, so first I'm going to fill in the truth table, and then we'll see what to do with it in order to verify the logical deduction. So let's start. Okay, so I want to do S implies T. So first line, they're both true. That's fine. Second line, they're both true again. That's fine. Third line, S is true, but T is false. That is not fine. I'm not okay with that for an implication. And then remember that when the antecedent of a conditional is false, the conditional is always true. So in the last four lines, S is false, and so the conditional is always true there. All good. T implies D, basically the same exercise. Okay, we can't have T be true and D be false. On the other hand, when T is false, we are all good. This one is fine too, but then in the sixth line, T is true, but D is false, not okay. And then here, false, or true, true again. Okay, great. So once we have our truth table filled out, what we do is we look for the lines where all of the premises are true. Okay, so I need to look in kind of rows and columns simultaneously here. So let's start with premise one. I see, okay, in the first row, premise one is true, premise two is true, and premise three is true. And, this is what's most important, the conclusion is also true. So this line is fine. This line says, hey, when the premises are true, the conclusion is true. What we need to look for in the rest of the truth table is any situation in which all of the premises are true, but the conclusion is false. So now if we go line by line, okay, so second line here, notice that in this line, one of the premises is not true. So I don't need to worry about this line. It doesn't matter what else is in the line. If one of the premises is not true, I ignore it. This line, one of the premises is not true. One of the premises is not true. One of the premises is not true. And in all the remaining lines, one of the premises is not true. So in this truth table, there's only one line where all of the premises are true. And fortunately for me, the conclusion is also true. That means that this deduction is valid. Whenever all of the premises are true, I am guaranteed that the conclusion is true. So, much in the same way that logical equivalences allow us to skip the truth tables in order to show that two expressions are equivalent, so do rules of logical deduction allow us to skip the truth tables when we're trying to figure out whether a deduction is valid or not. Unfortunately, the rules of logical deduction tend to have names that are even more obscure and mysterious than the rules for logical equivalence, so just bear with me and we'll do our best. So the first and maybe most important in some sense rule of logical deduction is called modus ponens. Modus ponens. Okay, so what modus ponens says is pretty straightforward. Modus ponens says, hey, suppose I have two premises. Premise one, P implies Q, and premise two, P is true. In that case, I can deduce that Q is true. So modus ponens says, hey, P implies Q and P. Those two statements together mean that Q is true. There's another one called modus tollens. Modus tollens. So modus tollens says that if one of my premises is P implies Q and the other premise is not Q, then it must be the case that P is not true either. So modus ponens and modus tollens really give you structure for working with implications inside logical deductions. So what I want to do now is I want to show an example of actually proving a logical deduction using these two principles. So we're going to go back to the logical deduction that we've been looking at. So S implies T, T implies D, and S. And what I want to show, and sometimes when you're working these kinds of examples, it's helpful for you to remember, I want to show that the conclusion D follows from these premises. Okay, so what I do now in order to use rules of logical deduction is much like working in standard form with a logical equivalence set of computations. What I'm going to do is I'm going to write new lines, and each time I write a new line, I'm going to justify how I got there in terms of the previous lines. So here's an example. I see that I have S implies T in premise 1, and I see that I have S in premise 3. And so modus ponens over here says, hey, I have the antecedent of the conditional. I can infer the consequent. I can infer T. So, in other words, my next line can be T. I'm going to call this line 4. And it's not a premise. Premises don't require justification, but this is not a premise. I need to justify it. So I'm going to write MP for modus ponens with premise 1 and premise 3. So I'm saying both what rule I used and what I used it with. I used modus ponens and I used it with premises 1 and 3. Now I can write another line. I'll call it line 5. And I'm just going to do the same thing again. I notice that I have T and I have T implies D. So if I use modus ponens again, I can infer D. And I did that with modus ponens. This time, one of the inputs to my modus ponens was line 4, and the other input was premise 2. And this is what I wanted. I wanted D, so now I'm done. So my logical deduction, the way for me to prove that all these premises, premise 1, premise 2, premise 3, imply D, is to use rules of logical deduction in order to get from this combination of premises down to the conclusion that I'm looking for.
So deduction gets really powerful when we combine it with quantifiers and predicate logic. So here's kind of a silly example, and then we'll do some more serious examples involving mathematics soon. So Lewis Carroll, so the author of books like Alice's Adventures in Wonderland, submitted these kind of nonsense logic puzzles to Laffan's Quarterly in 1896. So here's one of them. So he gives 3 premises. One, no ducks waltz. I think this is probably true. Premise number 2, no officers ever decline to waltz. Let's assume that one is true, or at least that it was true in 1896. And then premise 3, all of his poultry are ducks. So if you have poultry, then maybe you can relate to this, or maybe you can't. I personally don't have poultry. But in this little logic puzzle, premise 3, all my poultry are ducks. And so then from this, Lewis Carroll said, hey, from this we can deduce that none of my poultry are officers. None of the birds that I own are officers. This seems pretty reasonable as well. Question, can we actually get to the answer from the 3 premises using formal deductive logic? Well, to do this, our usual setup is that we need to define some predicates and sets. And so here we are. I'm going to define W of X to mean that X waltzes. I'm going to define O of X to mean that X is an officer. I'm going to define D of X to be the predicate, the statement that X is a duck. And then finally, I'm going to let P be the set of all of my poultry. Okay, so from this rather silly setup, we are ready to do our deduction. So I'm going to start by writing out what our premises are. Okay, so what are our premises? Premise 1. So for our first premise, we are going to have no ducks waltz. So we can write that as there does not exist x in my set P with the property that d of x, x is a duck, and w of x, x waltzes, are both true. Premise 2. There does not exist an element of P with the property that O of x, x is an officer, and not W of x, x doesn't waltz. So this is a translation of no officers ever decline to waltz. And then finally, premise 3. So premise 3, all my poultry are ducks. So for all x in my set of poultry, d of x, x is a duck. Okay, so now I have my premises. I am ready to undertake my deduction. Okay, so let's jump into it. I'm going to start by taking the premise 1 here, and I'm going to do quantifier negation. I have a negation symbol outside the existential quantifier, so I am going to move it inside. And that is going to give me, I'm going to call this line 1. So line 1, for all x in P, not d of x and w of x. So I moved the negation inside and I flipped the quantifier, and this is a quantifier negation rule. I'm using P1. Okay, next I'm going to keep going. Line 2. For all x in P, I'm going to move the negation inside the AND operator using De Morgan's law. So I get for all x in P, not d of x or not wx. And this is De Morgan's with line 1. Now I'm going to turn this into an implication. So I'm going to get for all x in P. So what I'm going to do is I'm going to use the implication rule backwards, and I'm going to get not d of x implies not w of x. So this is implication with line 2. Line 4. For all x in P, I can cancel these two negation symbols. D of x implies not w of x. So it's double negation with line 3. Okay, we are making progress because now line 5, for all x in P. So what I notice now is that I know, okay, first of all, I know that for all x in P, d of x is true, and I also know from line 4 that for all x in P, if d of x is true, then not w of x must be true. And so I can apply modus ponens in order to get the consequent w of x. So this is modus ponens using line 4 and premise 3. So from here, in order to keep the video a reasonable length, I'm going to skip a few steps here, a few intermediate steps. So these few intermediate steps are to get me from there does not exist x in P, such that O of x and not W of x, that's premise 2, these few steps are to get me to a simplification of that I'm using in these steps that I'm leaving out here just to keep the video short. I'm using, again, quantifier negation, De Morgan's, and an implication, and then double negation. And those steps are going to get me to, for all x in P, O of x implies W of x. So there are a few steps missing here to go from P2 to my line 6, and those steps I might ask you to fill in. So this is multiple steps with P2. Okay, and then once I have this, I am pretty much there because I have one more line, line 7. For all x in P, well, guess what? I have for all x in P, O of x implies W of x right here. And I have not W of x for all x in P in line 5. And so that means that by modus tollens, with line 5 and line 6, I can conclude not O of x for all x in P. And this is what I wanted. My conclusion, my answer, can be translated conclusion, no element of the set of my poultry is an officer, and I got there using a sequence of deductions with quantified logic. So as you'll notice, when I'm using quantified logic, this can be a little bit annoying. There's a lot of stuff to write here and a lot of steps, a lot of notation. But by being very explicit about all of my steps, really spelling things out, I can be confident that I have a correct logical deduction. There are lots of logical deduction rules, and we're not going to exhaustively hit each and every one in this set of videos. There are a few more that I would like to show you because they are especially useful, and we're going to use them all the time, formally or informally, when we think about the application of logical deduction to reasoning about mathematical ideas or algorithmic ideas. So let's take a look at just a few more logical deduction rules. So the first of these involve the conjunction operator. So these are pretty straightforward to think about if you kind of say them aloud. So here's one conjunction rule. If my premises are P and Q, I assume that P is true and I assume that Q is true, then I conclude that the compound statement P and Q is also true. Seems pretty reasonable. So if I have two premises, I can always stitch them together with an and. That's allowed. Here's another one. If I know P and Q is true, then I'm allowed to conclude that P, so I can always take the first argument of the and operator, and I can also take the second argument of the and operator. If I know that P and Q is true, then I can conclude that Q is true. So there's a few little tricks I can play, a few little small logical deduction steps that I can use in order to use the conjunction operator when I'm doing logical deductions. Here's some more interesting and complicated ones involving quantifiers, and these are especially useful. So the first of these is called universal instantiation, fancy word, use it at parties. So the idea of universal instantiation is that if I know that P of x is true for all x in a set, and I know that y is in that set, then I know that predicate P, whatever it is, must be true of y. If this statement is true for all x in S, P of x, and y is some element of S, then the statement must also be true P of y. So this is how I, in practice, use universally quantified statements in arguments. Here's another one. existential instantiation. Existential instantiation. So if I do existential instantiation, then this says, hey, if there exists an x in the set S such that p of x is true, then I can always sort of think about considering a specific one. I can say, hey, let's consider an element that I'll call y. I always have to give it a new name. So I can say, hey, let y be the element that I'm thinking about. That has the property that y is in the set S and p of y is true. So if I know that there exists an element of S such that p of x is true, then I can kind of say, hey, here's a new symbol y, and I'm going to let y be this element that is guaranteed to exist. There's at least one y with these properties. That's what there exists x and S such that p of x means. So let's think about it and use it. Then there's one more, existential generalization. So existential generalization says, hey, if I have my hands on an element y in S and I know that p of y is true, then one thing I can say from that is that there exists x in S such that p of x, because I literally have my hands on it. This requires me to have an element in S that such that p of x is true. And I literally am talking about it right now. I know it's there, and therefore I can conclude the existence claim. These are kind of abstract, all these guys on the bottom here, and so we're going to practice with them some when we're working with mathematical arguments shortly.